Okay, guys, so let's start. Let me make sure. Good afternoon, everybody. I'm not sure if the mic is working. Hello? Hello? I think it's working. Okay. Okay, let's start. I think someone is writing here something. Yeah, I can hear you. Thanks, Nicholas. So guys, today I'm gonna start chapter 5. In the very beginning of this course, in the first lecture or the second lecture, I told you the difference between microprocessor and microcontroller and microprocessor is microcontroller actually is a complete system. That's what I told you, right? It's a complete system. And you should understand what this means now better than the beginning, okay? Why? Now you understand inside the microcontroller, we have microprocessor, we have memory, we have ports, we have buses. Also, we have some circuits for external interrupts. You got what I'm saying? We have some circuits for the system tech. That's what we explained before. Also, we have some hardware for other things like timer, like analog to digital, like serial communication and other things. For sure, we don't have time to explain all of them, okay? So what I'm gonna explain in starting from today, what we have another component or another system inside the chip, it's called general purpose timer. That's what I'm gonna explain, okay? But there are other things like analog to digital, like serial communication. The good thing is to program these systems, all what we need, similar to what we did before. Number one, most of them needs interrupters, okay? I already explained interrupters, and the way, as you will see in the timer, the way you are gonna do interrupters is similar to what we did before. You got what I'm saying? Also, some of them for sure, or maybe most of them, they need external pins. Number two, in order to program all these systems, as I said, you need interrupters. Also, you need to set some registers, similar to what we did before. So what I want to say is, although I'm not going to teach you to choose the other systems because we don't have time for that, the way you are going to program them is similar to what we did. Just interrupt this, and you need to set some registers. Okay. So anyway, so today I'm going to start. We have a hardware here, a hardware circuit for timer. Okay. So I'm going to explain in this chapter. Number one, what is a timer? How can we use it? How can we program it and give us programs? Okay. So this is what I'm gonna do. So this is exactly what I'm gonna do in this chapter. Yeah, it's called general purpose timers. Okay. So here again, keep in mind the timer is hardware system here. Okay, inside the microcontroller. Okay, and this hardware system can interrupt the microprocessor. Anyway, as I'm gonna explain for sure in details. So in the first part here, I'm going to explain, okay, how can we use it? When, in what application, I'm going to say this problem needs a timer, okay? So that's what I'm going to explain here. How can we use it? Number two, how it works. How can we program it? And then I'm going to end for sure this chapter with program. So let's start with the first one, okay? Here, when in what application you need to say, yes, this problem needs a timer, okay? Actually, as you will see, the timer system is going to be used for one of two things. The timer system can do one of two things. Number one, it can generate output waveform or output signal, okay? And this is what we call output compare, okay, or pulse width modulation. Also, it can be used to measure time, a pulse width, okay? This is the only two things I'm going to explain, or this is the only two things the timer can do, okay? Number one, we have external pin, and I want to generate a square wave, okay? Someone can tell me, okay, but we already generated a square wave before, Okay, but this time here, the timer is going to generate a square wave, but efficiently. Yes, we did it before, but it took too much time from the CPU. You got what I'm saying? So here, I'm going to explain how the timer can generate a square wave, okay? For sure, with a certain frequency, with a certain duty cycle, but efficiently. Efficient, that means we are going to take a very short time from the CPU. Also, I'm going to explain it in some application, as I'm going to explain right now, we need to change the duty cycle, or we need to change the frequency of the signal easily, as you will see also now. In some application, we need to do that. Okay. So again, number one, the timer system can be used to generate a square wave. Okay. But efficiently. So that means we're not gonna take much time from the CPU. And this is very critical. Why? Because the CPU can take care of other things. Okay, as I explained before. Okay. Anyway, also that you can easily, on a very easy way, you can change the duty cycle, you can change the frequency, and this is needed in some application. I'm going to explain the application shortly. Okay, so this is one thing, and this is, by the way, if you are going to use this way, we call it, I'm going to use it as output compare, or you can say pulse width modulation. Pulse width modulation. Okay. So anyway, the other thing here, I can also use the timer system to measure time. What do you mean by measure time? I'm going to tell, and why you want to measure time? For sure, I'm going to explain. For example, I have a signal, I have something like that. I want to measure the time. I want to know what is the time here. Okay, what is the time of this pulse? Also, as I will see right now, I want to measure the time from here to here. In some applications, as I'm going to explain right now, we need to do that, measure time. Okay, guys. So conclusion: in what application we can tell, yes, we need the timer. Okay, you need the timer if you want to generate a square wave. Okay, efficiently, change the duty cycle efficiently. Also, if you want to measure time. So I'm going to give you for sure more details. So this is the main functionality of the timer. However, also, as you will see, also in this course, I can also use the timer like system tech, to generate periodic interrupts. Yes, this is not the main functionality, but I can also use it like system tech to generate periodic interrupts. You got what I'm saying? So now you already here have. I already explained system tech before, but still we can have more than one here in this chapter using timer. Again, also we can use it like external interrupts. Again, this is not the main functionality, but I can use it similar to external interrupts and also system tech. Anyway, so now I'm going to tell you what application you told us. There are some applications I need to generate a square wave efficiently. This is number one. Number two, in some application, I need to measure time. Okay. What are these applications? That's what I'm going to explain now. Again, the purpose of this section to understand why I need the timer, in what application I'm going to need the timer. Okay, so let's start with this application here. Okay, here ultrasonic distance sensor. It looks like something like this one. Also, I have another picture here. It looks like one like this one. Okay. By the way, I have several ones of this sensor. If you need it if you want to borrow it for your project, let me know and I can give it to you. Okay. So we have several of them. So so these sensors, okay, they are used to measure distance. Okay, how they are going to be used. If you see here, guys, this pin is going to be VCC. So this one is connected to 5 volt. Okay, this one is the ground, as you see here. So this one is connected to the ground. Okay, and now we have 2 pins, as you see here. This pin is called trigger. So trigger is connected here, and we have echo. Echo is connected here. Is actually here. Okay. So it's not connected. It's going to read it. Okay. So this is the story. Okay, guys. So we have only, as you see here, forget VCC, forget ground. So we have only 2 pins here. Okay. Every time you want to measure distance. Okay. You have to generate here a square wave this way, as you see here. So every time you trigger So this pin has to be connected to here. Okay, every time I generate a pulse like this one, this way, so actually you are triggering it to measure time. So what happens is that once you do that, once you put a screw wave this way here on this pin, as you see here, guys, we have transmitter and we have receiver, transmitter and receiver, and this is ultrasound. So it's a sound. And the main idea, before I give you more details, the main idea is that, as you see here in this picture, this is the sensor. So the sensor, we are going to send a sound. The sound is going to hit an object and then come back to you. Is that okay? Send a sound, hit object, and come back to you. Okay. So if I can measure the time for the signal to travel from here to here, if I can measure this time, I can calculate the distance. Why? Because there is a relation. What is the relation? The very basic relation is the speed of sound, which is known 340 meters per second. The speed of sound equal distance divided by t. Is that okay? So the distance is unknown. I don't know the distance. I know the speed. All what I need to calculate the time. That's it. What time? The time for the signal to travel from here to here. How much time it took? Is that okay? If I can get the time, I can plug in this equation to get the distance. Is that okay? So how we can do that? I'm going to tell you how. So what happens, guys, as I told you, we have here transmitter and we have receiver. So this one is going to synthesize a signal. When the signal come back hit, it's going to hit the receiver here. So what happens is that, as you see here, every time you want to do measurement, you have to generate a pulse like this one. Okay, you have to apply it here, this pulse. Every time you generate the pulse, what's going to happen is the device, the sensor itself, is going to generate a sound, ultrasound. It's going to transmit the sound. And once the sound is transmitted, it's going to pull the device or the sensor itself is going to pull this pin high, pull it back high. Okay? So once you send the sound, so this pin is going to be pulled high by the sensor. Is that okay? And then when the sensor receives the sound back, it's going to pull it low this way. You got what I'm saying? So again, the sensor itself, once the sensor transmits a sound, is going to pull this pin high. Okay. Once it receives the sound back, okay, so it's going to pull it low, pulse like this one. Okay, guys. So the time from here to here, this time here, the time from here to here, this is the time for the sound to go hit the object and come back. You got what I'm saying? So all what I have to do, guys, is that I need to measure this time. And then I have to divide it by 2 because this is the time to go and come back. Okay? If you can measure this time and divide it by 2 and then plug in this equation, you can easily get the distance. You got it, guys? Okay. So the problem now became number 1. All what I need to do, guys, in order to measure distance, all what I need to do, number 1, I need to generate a pulse like this one. I can do this one in the main program. That's easy to do it in the main program. Or you can do it using output compare. So you can use the timer to generate it, okay? Or you might not need the timer to generate it because this is actually trigger. So every time you trigger, you actually are going to do one measurement, okay? So it's not going to be continuous. Every time you want to do measurement, you have to generate a pulse like this one, okay? And now, the other pin here, the echo pin, there is a screw wave here. All what I need to know, I want to measure this time here. Is that okay? So, very easy. Every time you want to measure time, the only way to do it is input capture. Okay? So you need to use the timer for that. I told you the timer. The timer can be used for output compare, also it can be used for input capture. Every time you want to measure time, so input capture is going to measure time. How? That's what I'm going to explain in details. But every time in any application you want to measure time, input capture right away. Okay. So all what you have to do here, guys, I have to connect this one to the timer system. I have to use the timer system as input capture, as I'm going to explain in this section, in order to measure the time from here to here. Is that okay? Once you get the time, divide it by 2, and then you can calculate the distance. Any questions? Again, what I'm doing right now, guys, I'm just giving you some applications. Why I need to measure time? This is one application. Okay, there are other applications, and if you want to measure time efficiently, input capture. Okay. Okay, we have another application here. Why sometimes we need to measure time? I explained this one last time, guys, in the lecture. One way to measure the motor speed is to connect. You can attach a disc like this one. You can attach it to the motor, so that when the motor rotates, this disc is gonna rotate, and this disc is gonna rotate here between these two between these two devices here. So actually, one device here actually is an LED. The other one here is actually a transistor this way, as you see here, phototransistor. So as I said last time, guys, what happens is that so this is an LED, so this one should just transmit light or emit light. When the light, this is a phototransistor. This is how phototransistor works. When the light hits the base, so actually it's gonna connect the transistor. The transistor become like a short circuit, and then the output here is gonna become high. Okay, when it is dark, when there is no light, when it is dark, so actually the transistor is open circuit, and then I'm gonna get 0 volt here. Okay. Now, because here in this disc has 2 holes, as you see here. When there is a hole here, so actually the light is gonna hit the base, and then I'm gonna get 5 volt. And when it is solid, when the disc is solid here, so there is no light, transistor is off, I'm gonna get 0 volt here. So actually, for one rotation, for one complete rotation, I should get signal like this one. Okay, so this pulse is for this hole, this one for this hole. Again, is that here we use the disc has 2 holes. You can use more than 2 holes. That's okay. You can use 4, 5, whatever. It's still the same idea. Okay. So now, if I want to measure the motor speed, if I want to measure the speed of this motor, as I told you last time, there are 2 ways. You can connect this one to external interrupt, as I explained last time, in order to count how many. For example, here I'm gonna count how many rising edges we have in 1 second. So I'm gonna enable external interrupt for 1 second. Okay, enable it, and then every interrupt I'm gonna count. Interrupt 1, interrupt 2, interrupt 3, interrupt 4, and so on. So once you know how many rising edges we have in 1 second, I can divide it by 2, because for every rotation there are 2. So I can divide it by 2 to get the measurement. So this is one way. There is another way. The other way is, if you can assume for sure the motor has regular speed. Okay, the speed is fixed. So if I can measure this time for sure, if I can measure this time, I can calculate the speed for sure, because this is the time for half rotation. Okay, so again, this is just an application. For example, if I can measure the time from this rising to this rising. Okay, so if I can get this time, I can calculate the speed of the motor. Okay, so again, if you want to measure the time, so you can use input capture to do that. Different from what I explained before. Here, if you want to use it, so you have to capture rising and you have to capture falling, because I want to calculate the time between rising and falling. Yes, you can do that. So as I'm going to explain later, when you program input capture, you can tell input capture, I wanna capture only rising. I want to capture only falling. I want to capture both rising and falling. You got what I'm saying? So you have control. Okay. Here in this example, I have to capture rising only to measure the time from here to here, or you can capture falling edge only to capture it from here to. So again, this is another application to explain why sometimes we need to measure time. As you see here, guys, if I can just calculate the time from here to here, this is the time. This time is for one. Yeah. So here, this is half. So the time from here to here is half. So I have to multiply, because as you know, this is one hole and this is the other hole. So if it has only 2 holes, so from here to here, this is just half. So if you can get this time, I can multiply it by 2, and this is going to give you the time for one complete rotation. Is that okay? Any questions? Good. The other thing here, guys, also, again, I'm giving you many application. Why sometimes I need to generate square waves in some applications. I'm quite sure, I'm 100% sure in your capstone you need something like that, okay? Also, why sometimes you need to measure time, okay? So there is something, I'm not sure if you're familiar with it. I give you several videos. I don't have time here in the lecture to play these videos, but it's just very easy, okay? I'm gonna tell you the main idea, but you can watch the videos, okay? What is a stepper motor and how it is different from regular motor? In a regular motor, it's gonna rotate continuously, right? But for a stepper, you can tell from the English name, it's gonna rotate step by step, tick, 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 step by step. You get what I'm saying? So here, when you apply a pulse, it's gonna rotate one step, one step, one step, one step, one step, and so on, step by step. It's not gonna spin continuously. Okay, anyway. So the details are somehow with the details. I'm not gonna explain the details, but it's just very easy. The whole story is all what we need to do, you have to generate a square wave this way. That's it. So once you generate a square wave in a certain way, a certain square waves with a certain frequency, once you generate them and apply them to the motor can step, can step. Okay. So if you want to use the stepper motor, and by the way, so the stepper motor, it has too many applications. Like for example, if you have if you have the arm of a robot and you want to move it, okay, so they are very useful. They're used in too many things. Okay, if you want to, maybe I'm gonna run a video very quickly, but they have too many applications. At the end, without too much details, okay, for sure, if you want to know details, you can watch YouTube videos. But in order to, the conclusion is, in order to use them, all what you have to do, just generate a square wave. Is that okay? So output compare is going to help me to do that. Okay, output compare can help me to do that. Okay, because, and this is the most critical thing. Okay, I'm going to say it again because this is the most important thing. Okay, guys. In chapter 3, we generated a square wave. So why you want to generate a square wave again now? Big difference. Big difference. In chapter 3, we took too much time from the CPU, from the microcontroller. But here, most of the work is going to be done by the external circuit. I'm gonna take a very little time from the CPU. This is the main difference. You get what I'm saying? And as I said before, this is something desirable. Okay, that if every task you take a very little time from the CPU. That's something perfect. You know, guys, because I can make big applications. You got what I'm saying? So by the help of the hardware, most of the work can be done by the hardware. So that I'm going to take a very little time from the CPU, so that I can make big applications. CPU can do a lot of things. Okay. So anyway, so maybe I'm going to go quickly. I'm sorry, I don't want to spend much time on this one because I have a lot of things to cover. So maybe I just let's take one of them and try to see.
Imagine if manufacturing automation was simple. Introducing Vention. One button. This robot can mount these parts with high accuracy. Also, at any position within its workspace, this robot can hold its workpiece with full force, even at a standstill. So what kind of motor is used here? Indeed, this small robot uses stepper motors. Stepper motors can be classified as DC and synchronous motors. As the name suggests, these motors with a magnetic stator field can be created.
So anyway, so it has a certain functionality. So as you see here, guys, regardless of the details, you have, as you see here, you have several pins. The way you are going to generate a square wave here, it can control how the motor is going to step. Okay, but again, keep in mind, very useful. But it's going to be step by step. It's not going to spin all the time. Okay, you want to do it like step by step. Anyway, I think so. At the end, from the microcontroller point of view, I just wanna generate a square wave. Okay.
How does a robotic arm in a manufacturing facility repeat the exact same movements over and over? How does an automated milling machine move with such precision? It's all because of the stepper motor.
Stepper motor here, another one here, yeah.
What's special about the stepper motor is that it can control the angular position of the rotor without a closed feedback loop. It is a simple, accurate,
Look how it
and
steps,
open loop
step by
system.
step.
Let's first understand how the variable reluctance type of stepper motor works, which is the simplest one.
Okay.
Later on, you will
Anyway, I'm gonna leave this one to you, and if you are interested, it's not difficult to understand. You don't even need to understand the details. All what you need, how, for example, for sure, if you wanna learn everything, you wanna understand the details, that's okay. But what I'm saying, all what you need to know, how can you use it, okay? And the way you can use it is just as I told you, you just need to generate a screw wave, okay? So that's why output compare can be useful here. The other thing here, another application, why sometimes we need to generate a screw wave. This is another application here. Here, guys, you can control loads using varying voltage. What this means, varying voltage. You can change the voltage. Okay, how can you do that? As you see here in this picture, if you see here, guys, what happens is that, you know, when you have, for example, if I have 50% duty cycle, you know what is duty cycle? Duty cycle is how much this time T1 divided by total T, okay? So in case of 50%, that means this time is equal to this time. These two times are equal anyway, okay? So in case of 50% duty cycle, and this one is 5 volt, so actually the average voltage here is gonna be 5 volt divided by 2. You understand what I'm saying? This is the average voltage. However, if you have more, if you increase the duty cycle, if you have more than 50% duty cycle, so actually the voltage is the average voltage is going to increase. For example, if you have something like that, so here the average voltage is going to be up, it's going to be close to 5. Okay. However, if you have something like that, here the average voltage is close to 0. Okay. So again, so that's what I'm saying. All what you need to do is that by changing the duty cycle, in other words, by changing the time of the high, by changing this time, you can actually change the voltage, the average voltage. Okay. So as you see here in this figure, so as you see here, guys, for example, here the duty cycle is small. That's why the voltage, the average voltage is small. As we move this way, we actually are increasing the duty cycle because you can see the time of the high, the time of one is getting bigger. By doing that, so actually you increase the voltage. Okay. Okay. So you are telling me all what I'm going to do, I'm going to generate a screw wave and changing the duty cycle. And by changing the duty cycle, I'm going to change the voltage, the average voltage. That's true. Okay. So now how I can use it? Okay. So idea is clear, but how I can use it? Actually, for example, if you apply this one, for example, to a motor, so actually when you increase the voltage, you are going to increase the motor speed. You get what I'm saying? The more you increase the voltage, you can actually increase the speed of the motor. Same thing if you apply it to a bulb, okay? For example, as you see here in this figure, so actually, the more you increase the voltage, you are going to increase the brightness or the intensity of the light, okay? So, or it can be more brightness, okay? So this is the main idea. The more. So that's what I'm saying. For some loads, like the motor here, and also for like the bulb here, for some loads, the more you increase the voltage, okay, we need to do that. Increase the voltage, decrease the voltage. Okay. For example, here you can make this light dim. You can make it dim, or you can make it more bright, or also so you can actually control the intensity of the light. Or here you can control the speed. Okay, guys, any questions? So I need, in order, if I want to do application like this one, guys, if I want to do application like this one, I need an easy way, because this is the secret. Okay, guys, everything I'm going to explain in this chapter, I can do it using the knowledge of chapter 3. I can do it using the microprocessor. Okay, however, this is not a good thing, okay? Because I'm going to take too much time from the microprocessor. You get what I'm saying? So the beauty of this part, or the most important thing in this chapter The hardware will do most of the work. So I can do these things. We're going to take a very little time from the CPU. This is the most important thing. So I need an easy way to generate a signal and also to change the duty cycle easily, very easily. That's what you are going to see in this chapter. So you are gonna know the details, but as you will see in this chapter, you just have a register. You have a register here. When it changes the number in the register, you just change the duty cycle. That's it. That's all what you need to do. That's why I'm keep repeating easy way, because it's very easy. You know what I'm saying? You don't need to care. You don't need to care about anything more than that. Just you have a register. When I increase, as you increase the number here in this register, you actually are going to increase the duty cycle, and thus you can increase the voltage. Okay. So, but the signal itself is going to be generated by the timer system, by the hardware of the timer system. Any question? Okay, let me, before I move to the next section, let me tell you the conclusion. The conclusion is, number one, what I'm explaining here, guys, inside the microcontroller, we have a hardware circuit. This hardware circuit, we call it a timer or general purpose timer, okay? And this timer can be used for one of two things. Number one, it can be used as input capture. Input capture means you want to measure time, okay? Number two, it can be used as output compare, okay, or pulse width modulation. And in this one, you can generate a square wave efficiently. You can actually change the frequency easily. You can change the duty cycle easily, because in some application, I need to do these two things, okay? Any questions? Okay. Now I'm going to explain how the system works, how you keep saying the hardware will help me. That's what I said. What I said, the hardware will help me to do it, okay? But how it is designed, okay? And how I can use it, okay? So here I'm going to explain how the timer system works, and then I'm going to explain how can you program it, and then I'm going to give you program. So let's start with this one, okay? How the timer system works, okay? Number one, as you see here, we have free run hardware counter, independent of processor. What free run means? What independent of the processor means? Okay, let me say. This is similar to system tech counter. I told you when I explained system tech, I told you we have a hardware. This hardware, we call it a counter. In digital system class, you should have designed something like that. Okay, so there is some hardware. It has a number of flip-flops. Okay, and then this one is just a counter. It counts. So it has an input clock. It has a clock this way, so that for every cycle is going to increment the count by 1. Okay, for example, if this counter is 3 bits, for example, if it is 3 bits, what's going to happen in the very beginning, it is 0, 0, 0. Okay, so it has 3 flip-flops connected in a certain way. I don't need to explain too much details. So it's just a hardware. This hardware has clock. Okay, and it has, for example, if this counter is 3 bits, it should be this way. After one cycle, this flip-flop should be 1 this way. Okay, another cycle. So every cycle here is going to increment the count by 1. Okay, and by the way, we have up counter to count up, and also we have down counter to count down. So some of them can count up, some of them can count down. So now after another cycle, so it's going to be 1 here. Another cycle should be number 3. Another cycle should be number 4. Okay, another cycle number 5. Okay, another cycle number 6. Okay, another cycle, okay, should be number 7. Another cycle after 7, it goes back to 0 again and repeats. Yeah, that's how it is. Okay, so this is how it works. So guys, what's going to happen is that we start from 0, 0, 0, and then it's going to every cycle from the clock is going to be incremented by 1 all the way until 1, 1, 1. After 1, 1 is going to go to 0, 0 and repeat again. Okay, guys, it's a hardware. And again, when I say independent of the processor, what it means? It means the processor does not need to send anything to run it. Okay, this is a hardware system. It's running by its own. The processor does not need to do anything to run it. Okay, other than configuration. You are going to do some kind of configuration. Once you do the configuration, the hardware is going to run it by its own. Okay. Anyway, so what I'm saying here, guys, in the timer system here, we have number one, we have a hardware counter. Okay. This counter can increment or decrement as I'm gonna. This is something you can control. You can, similar to what we did before. So you need to do initialization. We have a set. You have a set of options, and based on what you want to do, you can select what do you want to do. Okay, based on the application, so you can select the counter can count up or count down, or count up and then count down. So you have some options. So I'm gonna explain them for sure. This is something you can do. One more thing, guys, here, the counter here is 16-bit. For sure, I give you a small example. I told you 3-bit. That's just a small example. But this one, 16 bits. That means this one can count from 0, 0, 0, 0, 16, 0 until 16 ones. You remember 16 ones should be 65, 5, 35. So this one should count from 0, from number 0 until 65, 5, 35. Okay, and then go to 0 again, and so this is how it works. Okay, so the counter runs continuously. Okay, and then what else do you have here? The counter restart automatically when the counter reaches to 0. I'm going to explain what I mean here. The software you can do initialization to this counter. Okay, wait a second. What I'm saying is that we have a counter. I'm going to explain, okay, what is the relation? You have just told us you want to do input capture, you want to do output compare. Input capture means you want to measure time. And now you are talking about counter. What is the relation? For sure, there is a relation. That's what I'm going to explain for sure. So we have a counter. This counter is going to support input capture and also support output compare. How? Wait, be patient. The details are coming. You got what I'm saying? So this is a part of the system. So I'm going to explain how I'm going to use the counter to do input capture and output compare, because this is the purpose of this chapter. This chapter is, I'm going to explain how can we do input capture and output compare. Okay. So to do that, I need support from a counter. So we have a counter here, as you see, guys. This counter is 16-bit, as I told you. Okay. It continuously run. Also software, or you can do some initialization to control control the clock. Okay, so as I told you guys, here we have a clock here. For sure, the higher the frequency, what it means? It means it's going to count fast. So the lower the frequency, so it's going to count slow. You got what I'm saying? This clock is the input clock here. Okay, because 1 over f is going to give you the time for one count. 1 over f is the time for one count. So to increment is a count or decrement, it depends on how you are using it. Okay. For example, to increment is a count by 1, I need this amount of time, 1 over f. Okay. For sure, I'm going to explain how can you control it and why and so on. Okay. But anyway, so the software can select the frequency of this one. Okay. So here, for our counter, we have 3 modes. We have 3 modes for the counter. Okay, we have up counting, down counting, center aligned counting, and you can select them by programming during the initialization. What it means, I'm going to tell you what it means. So look at these nice figures. So what happens is that if you see here, guys, for example, if I select up counting modes, if you select up counting modes, how it works? So the way it's going to work, the counter should count from 0, go up until a certain value. We call it auto reload value, or ARR. Okay, ARR. Okay, and then after that, automatically it's gonna come to 0 and count again until ARR. 0, count again to AR, and so on. For example, number 1, let me ask you a question. What is the maximum value for ARR? What is the maximum value? Can anyone guess? It's a 16-bit counter. It cannot be more than 11111. Is that okay? So the maximum value should be 65,535. That's true. It cannot be more than that because it's a 16-bit counter. Okay. However, you can make it less if you want. You can make it less. For example, if I make it 1,000, for example, so what's going to happen? This one is going to count from 0 until 1,000, and it's going to go to 0 again to 0, 1,000, 0 to 1,000, 0 to 1,000, and so on. Is that okay, guys? Again, until now, be patient with me. I'm just connecting piece by piece. I'm just explaining how the counter works. I didn't explain how can you use it to generate output, to make output compare with input capture. But this is a very important component. We need it. I'm going to explain for sure how. So this is if you want to use it in up count. Okay, so what is RR? Very simple. We just you can write whatever you want to write in this register, but you have to keep in mind whatever you want to write here is actually should not be more than 65,535. This is the maximum you can put here, okay? And by the way, this is the counting period or counting period. So the time from here to here. So here, guys, what happened? Okay, I told you this one is gonna count from 0 until the counting until ERR. So how many counts you did here? 1 plus ERR, right? Because you start from 0. You start from 0 until ERR. So how many, this are the number of counts. And what is the time for each count? The time of each count is 1 over the clock. Makes sense? Because it's going to increment every 1 cycle of the clock. That's why I'm going to multiply it by 1 over the clock. So this formula here should give you the time from here to here. Very simple, very simple. How many counts? How many counts you are going to do? And what is the time of each count? You multiply them together, you get the time from here to here. Okay, guys? This is if you want to use it like up counting. Is that okay? There is another mode. And as I told you, it's a very simple. So again, you can ask the counter to count this way. Or you can ask the counter to count in a different ways. I'm going to explain them right now. How can you do that? During the initialization. When the time comes, I'm going to tell you there is 1 bit. If you put 1 in this bit, it's gonna count this way. If you put 0, it's going to count this way. Is that okay? And then I'm going to tell you, does it matter count this way or that way? We'll see. We'll see later how this is going to impact how this is going to impact the signal you want to generate. Okay, for sure there is a link, but the other way here we call it down counting. As you see here, guys, this one is similar to this one, but the difference is that here I start from 0 and then increment 1 for every cycle, increment 1 until ERR. Once I reach it to ER, it's going to go to 0 again automatically. You don't need to do anything. The hardware will do that, okay? And then count again, okay? The other way, here's the opposite. So here I'm going to start from ERR, as you see here. Then this is, we're going to count down. So every time decrement. You got them. So if you start from, as you see here, I give you some example here. So for example, if ERR equal to 4, so it's going to be 4, after 1 cycle, 3, after 1 clock cycle, 2, 1, 0, after 0, automatically, I don't need to do anything. It's going to go again to, so what's happening here is that you have, this is the counter, guys, okay? The counter, as I told you, it has a number of flip-flops, okay? So the count itself, the count here is actually a register. This register is called CNT. Okay, so if you wanna know what is the count right now, okay, just a register. This register is called CNT. What happens is that automatically, once this one comes to 0, here we have ERR. So once we come to 0 here, so the hardware is gonna copy whatever here, put it here, so that you can decrement it again automatically. It's the same thing here. It's the same thing here. So here we have, this is the counter CNT. Okay, what happens here? Once you reach to ERR, so once they are equal, okay, so what can happen here? So the hardware automatically is going to clear this one to count again. Once it's equal, it's going to clear it and so on. Okay. Anyway, so any question? So this is if you want to use it. So at least listen to me. So what I'm saying, we have counter. This counter needs a clock, right? For every cycle, it's going to increment or decrement. Is that okay? Number 2, I told you we have a register called ERR. ERR can tell you want to count from how much time is going to count from here to here. Okay, this is called ERR. Okay. Also, I told you there is a register called CNT. We're going to need it later. This CNT can give you the current count. What is the current count right now? Okay. There is another mode. I'm going to, the last mode we have, we call it center aligned counting mode. Okay. As you see here, guys, what's happening here, for example, is gonna count from 0 increment until ARR. Again, don't be confused. ARR is just a register. You can write whatever you want to write here. If you want to count to 100 or 200, 300, whatever you want to do. Okay. So here you can count up until ARR, and then it's gonna decrease until 0, and then it's gonna repeat again. Okay. Anyway, so I'm gonna give you details, but for now, at least you can know we have three counting modes. Okay. It can count up, it can count down, it can count up and then down. Okay, guys. Any questions? Again, this is just a free running counter. Okay. How we are going to use it to generate a signal? Details are coming. How we are going to use them to measure time? Details are coming. But this is going to help. It's going to support input capture or output compare. Okay. So let's come to the idea of output compare before I give you. Let's come to output compare. What is the idea? How it works? Okay, this is the way it works. Look here, guys. Again, as I told you, we have a counter here, hardware. Okay, processor does not need to increment the count by 1 or something like that. It's a free running, independent of the processor. Okay, so the count CNT register. This register should give you the current count. What is the current count? Okay, and then you have a clock here, as I told you. This is the counter, as you know. Okay. So what happens is that, look here, guys, we have another register. This is, now I'm going to link. Listen to me. What I'm going to do right now, I told you, we need to do output compare. I told you to do output compare, we need counter. Okay, but how? That's what I'm going to answer now. So now I'm going to link how the counter is going to be used to generate signal for output compare. I'm going to link it now. So what happens is that, guys, we have another register. This register is called to compare and to capture register, or CCR. Okay. What happens is that once the count here is equal, this is how the hardware will do it. Okay. So we have a register. This register is called CCR. Okay. And we have CNT. CNT is the count. So the CNT is incremented because this is the count. Okay. Once they are equal, once is the current count, if the current count in the counter is equal to CCR, as you see here, two things are going to happen. So, for example, okay, make it easy. I'm going to make it easy. For example, if I use this mode, okay, if I use this mode, and then I'm going to say ARR is 1,000. That's okay. And then I'm going to say CCR is 500. So, for example, 500 is here, 500 here. Is that okay? 500. So what's going to happen at this moment, something will happen. When the current count CNT is equal to CCR. Also this moment. Okay. So once CNT, the current count equal to CCR, again, CCR is just a register. You can write whatever you want to write. Okay, but I'm gonna elaborate later. But they just a register. At this moment, two things are gonna happen at every moment. What are the two things? Number one, interrupt is triggered. It's number one. Number two, action should be taken on the pin because there is a pin. I told you, if you want to use output compare, there should be some one pin, right? Because this pin I'm gonna generate a signal on a pin, right? Or if it is input capture, so there should be a pin here so that you can connect the signal. I want to measure the time. So either output compare, input capture, there is a pin, right? So anyway, so again, so what's gonna happen here, guys? At this moment, every time the count is equal to CCR, a register CCR, two things are going to happen. Number one, action is going to be taken on the pin. Number two, interrupt is triggered. Okay. Same thing here. If I put CCR here, if I put CCR this way, so again, here at this moment when it is equal, okay, interrupt is triggered at every point. Action is going to be taken on the pin. Okay. Same thing here, but here one here and one here. So every the time equal. So in this case, action is going to be taken on the pin, and also interrupt is triggered. What do you mean by action is going to be taken on the pin? What do you mean? Okay, what I mean, this is something you can program. We have a table here. So it depends. Again, this is something you can program. For example, let's take the very easy case. The very easy case, I can say toggle. So there are 3 bits. This is something you can initialize. So there are several actions. You can decide what you want to do. For now, let's talk about the very simple case, toggle. Toggle means you are going to flip the bit. So what happens, I think I should have I have a very nice. Now, I'm going to link the counter to output compare. How? I'm going to tell you how. So what happens here, this is the counter. As I told you, the counter is going to count from 0 until ERR. Send from 0 until ER, from 0 to ER. That's okay. And now I have another register. I'm going to call it CCR. Okay. I told you every time it's equal here at this moment here, 2 things should happen. 2 things. Number 1, interrupt is triggered. Number 2, action should be taken on the pin. If I can select the action to be toggle, you want to toggle the pin. That's what is going to happen to the pin. So what's going to happen to the pin, to the external pin is, if you see here, guys, the pin is 0. Once we come here, I'm going to toggle to high. Once I come to here, I'm going to toggle. Once I come here, I'm going to toggle. I'm going to toggle and so on. So by this way, I can generate a skew wave. Okay. As I'm going to explain later in details, I can generate this skew wave without using the interrupt. So I'm not going to use the interrupt. Is that okay? If you don't use the interrupt, so how much time do you need? If you do this way, how much time do you need from the CPU? Nothing. I don't need it. And this is the interesting part. So I don't need any time from the CPU. Okay. All what I need from the CPU just to do the initialization. This is the most important thing, okay, to understand. I'm going to say it again. If there are 2 ways to use it, as I'm going to explain later in details. In one way, I'm not going to use the interrupt, okay? In this case, all what I need from the CPU just to do the initialization. Once you do the initialization, the hardware is going to take care, is going to generate the skew wave by its own. How? This way, as you see here. The timer is going to count this way. CCR, you put some value here in CCR, okay? And then the output is going to be toggled this way. Very interesting. You got what I'm saying? So after you do the initialization, this signal is going to be generated, okay? Without or it's going to be generated independently from the processor. The processor doesn't need to do anything. You remember in chapter 3, what we did? Number 1, the processor has to pull the pin high. Number 2, the processor has to count for 1 second. Number 3, the processor has to pull the pin low. Number 4, the processor should count for 1 second, and then we have to repeat. I need it in chapter 3. I needed 100% of the CPU time to do it. Okay. Now, after the initialization, I need zero time, because everything will be done by the hardware circuit here. You got what I'm saying? So once I do the initialization, the circuit by itself, the counter is counting this way. Once it is equal, I'm gonna toggle the pin. Okay. Once it is equal, I'm gonna toggle the pin. Once it's equal, I'm gonna toggle the pin, and so on. Any questions? For sure, the details are coming. Okay, but I just want you to understand, as I have just explained. Number 1, I'm going to use for output compare, I need to generate a signal. To generate a signal, I need a counter. And now I make the link. I linked it. How it works, as I told you here, this is the counter is counting this way, and then there is a register, we call it CCR, and then every time it is equal, there is an action. You can select what action you want to take, but at least, so what action you have here? Okay, for example, one action, if you put 0, 0 here, again, this is just initialization. We have 3 bits. I'm going to explain later. We have 3 bits. You can select whatever action you want to take. Sometimes for some reason, as I'm going to explain later, I can say no change. I don't want to change the voltage on the pin. Okay, if you want to do this way, put 0, 0, 0. Another one, I want to pull the pin high. Okay, so you have to select this one. Another one, I want to pull it low. So I want the pin to be low. Okay, anyway, forget the details. The details are gonna come later, but at least the easy way now, just to use it, I'm gonna select toggle. Toggle means you flip the bit every time the register CCR is equal to this. Any questions? Okay, guys. Now, so yeah, here I'm just explaining to you guys here, as you see, we have counter. This counter has a clock, as you see here, input clock. This clock, as I'm going to explain later, this clock is actually generated. We have here the system clock. This is the system clock, which is around 2.08 or 09, something like that, megahertz. This is the system clock. And then I'm going to divide it by some value. We call it prescale. So for example, if I make the prescale, whatever, 100, so you are going to divide, and this will be the clock. Okay. So the prescale again is just a register, and this is a part of the initialization. Okay, guys. So the input clock here is 2.08 megahertz. You are going to divide it by a certain value. We call it prescale. This is a prescale. You can select it, just a register, and then this will be the clock, the clock of the counter. Okay. This is one thing, and also as you see here, guys, as you see, we are going to compare this count. I'm going to compare it to CCR. Every time it is equal, two things should happen. Action should be taken on the pin, and also you trigger interrupt. Is that okay? One more thing, okay, to complete the picture. Okay, one more thing. Also, the counter itself also can trigger interrupt. Okay, again, it depends on how you use it. So I'm going to show you later. I'm going to use it in a certain way so that I don't need the interrupts. And then I'm going to also show you if I want to use interrupts or how I can do it. Okay, but again, what I'm saying, this is how it works, how I'm going to use it in details. That's what I'm going to do later. But the way it works is that, as you see here, guys, interrupt can be triggered when it is equal. This is if you use it output compare. Okay, input capture is different. Now I'm explaining output compare. So once the count here is equal to CCR, okay, interrupt is triggered. But also there is another interrupt that can be triggered from the counter or timer itself. What is this interrupt? I'm going to go back and going to tell you. Look here, guys. Here, okay. So here, every time this one go to here and then go to 0, that's what we call overflow. At overflow here, also interrupt is triggered. Okay, guys? So there is another interrupt. So this is interrupt. So there is another interrupt here because of overflow, and another interrupt. Every time there is an overflow, the timer is going to trigger interrupt. So now we have two types of interrupts I explained right now. Number one, the timer is going to trigger interrupt every time there is an overflow. Okay. How can we use it? This is something I'm going to explain later. In some, I can use the timer in a certain way so that I don't need them. Or I can need them, but let me complete how it works. And then how can you use it? This is something different. Okay. So the way it works is that, as I explained to you guys here, every time there is an overflow at this moment, interrupt is triggered. Do you need it? Yes, sometimes I need it, sometimes I do need it. So I'm going to explain it later. But there is interrupt is triggered here. Also, there is another interrupt is triggered from every time CCR equal to CNT, another interrupt is triggered. You got what I'm saying? Also, if you count here in this case, if you count down, so interrupt is triggered here when it is underflow. There is no overflow here, underflow. So here interrupt is gonna come from here. If you select this counting, if you select this count, so interrupt are gonna come here. If you select this counting here, so interrupt is gonna be one here and one here. Okay, guys. So let me tell you the conclusion. So the conclusion is that number one, the counter itself is gonna trigger interrupt every time there is underflow or overflow. Okay. This one is called underflow. This one is called overflow. Okay. Do you need it? I'm going to explain later. Sometimes yes, sometimes no. But this is how it works. Number two, every time CCR equal to CNT, as I have just explained, another interrupt is triggered. Okay. Yeah. So here, interrupt here, interrupt here, interrupt here. Any questions? Okay. I'm going to explain for sure in details pulse width modulation mode, but here somehow this one is somehow different from what I did here. I just want to link. I want to link between the counter, because we have counter that's counting, and we have signal we are going to generate. So what is the link? That's what I want to do. So here I did the link here. I did the link by selecting toggle. So every time this one is equal, toggle as you do here. However, we have other modes. So for example, here, as you see here, guys, we have toggle, we have pulse width modulation, and so on. Okay. For example, here in pulse width modulation, it's somehow a little bit different, but now I'm going to show you the link. For sure, the details are coming. For example, look here, guys. This is how it works. It's different from toggle. Again, this is different mode. You can use it in different ways, and then you can select the mode that you need in your application. But we have different modes, and then you can select the one you need for your application. Okay. So for example, if you want to use it in pulse width modulation mode 1, how it works? Okay. Look, this is how it works. Always is going to toggle here. Always, no matter what, it's going to always toggle here. Okay, as you see here in this picture. Every time there is this one is going to toggle. We didn't have it here. What we have here, the toggle always was here. Okay, because this is a different mode. Also, every time this one is going to toggle actually twice. So every time here and here. So as you see here, guys, it's going to be 0, 0, 0, and then once we come here, it's going to toggle to high. Once to come here, it's going to toggle to low. 0, 0, toggle high, toggle low. Is that okay? And now I'm going to come to the interesting part. Very interesting part. What is that? I told you I want to use output compare to generate a signal with different duty cycle easily. That's what I said. Easily. So all what you have to do, guys, if you want to change the duty cycle, just I'm going to change the location of CRR. Because if CRR is this way, so actually this will be the on period. But if I bring it here, so this will be the on period. You got what I'm saying? So easily you have a register. So conclusion, after all what I explained, conclusion, you have a register. This register is called CCR. Okay? CCR should take a value. CCR should take a value from 0 until ARR. Remember, the maximum is ARR. So CCR should be something between 0 and ARR. And as you increase CCR, as you increase it, so actually the duty cycle is going to be less, as you see here. So for example, here in this example, if I put CCR here, so actually this part is going to be the high part. But if I put it here, so now you can see the signal is bigger. Here's the average voltage is V divided by 6. Here's the average voltage is V divided by 2. You got them. This is the beauty of it. The beauty of it is, again, this is the most important thing. Processor microcontrol. Again, I'm gonna refer to chapter 3. In chapter 3, the processor has to flip, has to toggle. Every sometime the processor has to flip. Now the processor don't need to do that. The hardware will do it for you. This is how it is. This is the most important thing. Okay, so that's why the processor can be free to do something else. Okay. However, all what I need from the processor is just you can change CCR. So you need an instruction. In this instruction, you can just change CCR. I'm going to write a certain value in CCR. And by changing CCR, I'm going to change the duty cycle easily. That's all what I need from the CPU. All what I need from the CPU. Number one, do the initialization in the beginning. Just number one. Number two, every time you want to change the duty cycle, just write something to CCR. That's it. Everything is done by the hardware. Very interesting. Okay. Any questions? Okay. Until now, again, until now, I link it the counter to the generated signal, okay? I didn't yet explain how can you use interrupts. Again, as I said, I'm gonna give you examples to generate signal without using them. So you may not need interrupts, okay? But you should know that you are gonna have interrupt here. Every overflow, we have one interrupt, and also every time it is equal, sorry, here and here and here. Every time it is equal, also we have another interrupt, okay? Sometimes you need them, as I'm gonna explain later, but anyway. Yeah, so this is actually, if you wanna use this one, you can generate different signal. Forget the details for sure are coming, how can we use it, okay? Any questions? Now, I wanna talk about input capture. I told you input capture is used if you wanna measure time. So how I can measure time? And how the counter is gonna help me? Because I told you the counter is gonna support input capture and output compare. I'm gonna tell you how. Very simple, very, very simple. Look here, guys. In case of input capture, we have each detector hardware circuit, and we have a pin here. So there is a pin here, a pin, and we have each detector circuit, similar to external interrupt. Remember when we did external interrupt, okay? So the processor did not need to do anything to check if there is falling or rising edges. This is done automatically by the hardware. The hardware will detect if there is rising or falling edges, okay? And then once there is rising or falling edges, the hardware is gonna interrupt the processor. That's what I explained in chapter 4. You got what I'm saying? So the processor does not need to do anything to check if there is rising or falling, right? It does not need to do pooling, as I explained before, right? So anyway, so same thing, we have here each detector. Okay, that's okay. And if I ask the circuit to capture both rising and falling, I told you this is something you can program. You can ask, I want to capture only rising, I want to capture only falling, or I want to capture both. Let's have this example. I want to capture both, for example. So I want to capture rising and falling. Okay, if I want to do something like that. Okay, so what's gonna happen? How the counter is gonna help me to measure time. Okay, the way it works is that, look here, guys. I think I have a very nice figure here. Okay, let me explain it. Okay. Look here, guys. Okay. Here, I want to capture, I want to measure the time from here to here. How can you do that? How the counter is going to help you? I'm going to tell you how. Look at the idea. The idea is that when this one came, look at the counter. The counter was number 70. So this one came at count number 70. And when this one came, the counter was for example, 90. Because the counter is working, right? So every one clock is going to increment by 1. Okay, guys? So what's going to happen? All what I need to know, what was the count here, what count, and what was the count here. And then I have to do some calculation to know how many counts it took to count, how many counts are from here to here. So if it took 20 counts, so from here to here, the counter counted 20 times. So from here to counted, because the count here at this moment, the count was 70. At this moment, the count was 90. So if I do some calculations, I can know from here to here, the timer counted 20 counts. If you can know how many counts you have, can you convert it to time? Very easy, very trivial, because I know the time of one count equal 1 over the clock. I already know what is the clock, right? So if I know how many counts from here to here, how many counts the timer counted, it's easy, I can convert it to time. Because every count should equal 1 over clock. So I can take 20 times 1 over the clock. This should give you the time from here to. You got it? So here, this actually, you are going to get the time, but in number of counts. Okay, guys? So this is the main idea. So the main idea, all what in order to measure the time from here to here, I need to know what was the count here and what is the count here. Because the counter is running independently. Okay, so it's gonna be running. So how this happens, I'm gonna tell you how. This is exactly what input capture is doing. So what input capture is doing, guys, is that, look here. We have, this is the counter, okay? We have each detector. If I ask the each detector, okay, each detector, I wanna count, I wanna capture rising and falling. Okay, so when rising comes, or falling comes, if any one of them comes, what's gonna happen is that the hardware is gonna read whatever number you have here, the count. It's like timestamp. This is a timestamp for this one. Okay, is gonna read this one and put it where in CCR. And then it's gonna trigger interrupt, so that in the interrupt subroutine, you have to take whatever here and save it somewhere else. Okay. Again, so what I'm saying, every time there is an event here, rising or falling, what's gonna happen is that the value of the count here, the timestamp, this is like a timestamp, the value of the count here is gonna be stored in CCR, and then it's gonna trigger interrupt. Why it has to trigger interrupt? Because you have to take this value from CCR and save it somewhere. Otherwise, if you don't do that, it's going to be overwritten. So once another edge comes, it's going to overwrite it. Okay, guys? So let me tell you the conclusion. The conclusion is that in case, I'm going to do it very slowly, okay, so that you can understand it. Look here, guys. In case of output compare, every time the count here is equal to CCR, and in this case, you have to write to CCR. In this case, you have to write to CCR. Every time the count is equal to CCR, two things are happening, should happen. You trigger interrupt and action is taken on the pin. Is that okay? This is for in input capture. Output compare, the story is a little bit different, okay? In output compare, as I'm explaining here, okay, so as I'm explaining here, guys, here, every time there is an event, okay, and you can program what do you mean by event. You want to capture only rising, you want to capture only falling, or you want to capture both. Every time there is an event, the hardware automatically is going to take the current count, store it in CCR. This time you have to read CCR. Don't write to CCR. You cannot write to CCR. Hardware is going to write to CCR, and then you can read it. Read the value. This is a timestamp for this event. So two things are going to happen here in case of if you program it input capture. Two things are going to happen. Number one, the count is going to be stored in CCR. This is number one. Number two, interrupt is triggered. Okay. So I'm going to give you some examples to understand it. Okay. Number one, guys, here. If I want to, for example, here, I want to capture rising and falling. Okay. So if the signal comes this way, so we have rising here and we have falling here. Or we have falling and we have rising. That's okay. I want to measure the time from here to here. What's going to happen, guys, is that, again, this is something you can program. If I do initialization or I do programming and ask the hardware to capture both rising and falling, okay? Once you have rising or falling, okay, the time, which is the count, what is the current count? Which is the count. So this count is going to be stored in CCR. Interrupt is triggered. You have to take it from CCR, store it somewhere. If you don't do that, it's going to be overwritten here. We have only one CCR. Every time there is event, it's going to write to CCR. Every time there is an event, it's going to write to CCR. Is that okay? That's why we need interrupt now. So what's going to happen here is that every time there is an event, the count is going to be written in CCR. Interrupt, okay? Same thing here. Once you know what was the count here, you can simply do some calculation. You can get the difference, whatever, to know to get the time, how many time it counted here. Okay, we have another example. For example, if I capture only rising or only falling. So if you have something like that, guys, if I capture both rising and falling, so I'm gonna get the time from here to here. Okay. However, if you have a signal something like that and you capture only rising, so I'm gonna get the time from here to here. If you capture only falling, so again, this is the example I'm giving you here. So the example, oops. So here, just 1 minute, 1 second, sorry guys. Yeah, just 1 second. So here, what I'm saying here, guys, is that, yeah, if I capture only rising, okay, so what's gonna happen? I'm gonna get the time here. I'm gonna get the time here. Once you know what was the count here, what was the count here, you can do the calculation to see how many counts the counter counted from here to here. Same thing here if you capture falling. Okay. So I give you very nice example here. This is similar to what I explained. Look here, guys. If here I want to capture only rising, or I programmed the hardware to capture only rising. Here I make ARR 99. So what's going to happen? It's going to count to 99, then 0, 99, 0, 99, and so on, as you see here. Assume the signal came, one rising came here, and the count was 30. So at this moment, 30 is going to be written in CCR and interrupt is triggered. In the interrupt, I have to take this one, store it somewhere. Otherwise, it's going to be overwritten. Okay. Another one came here at this moment. So another interrupt is going to happen here. Once you have another interrupt is going to have here, and this number is stored in CCR. Okay. Once you have these two numbers, here it was count. The count was 30. Here the count was 63. You can do very simple calculation to calculate the time from here. The time is number of counts. That's why if you see how it is written here, in this, again, this is a very simple example. This is just a very simple example. I'm saying here, this one is 63, 30. I'm going to do just subtraction, and then I'm going to get 33 in time units. Time unit. What do you mean? It's not in second. It's not in second. Number of counts. That's why I'm saying time unit. And again, this is a very simple example. Why? Because what if the signal is too big? I'm going to start here, and then I'm going to end here, for example. So it's a signal is like too big. You got what I'm saying? So how can this is another complicated scenario. I'm going to talk about it later. But now I'm considering a simple example. I started here, I ended here. What if you start here and then you are going to end later, for example, here? So in this case, I need to know how many overflow happened in order to do correct calculation. The last thing, just one second. The last thing I want to teach here, guys, is that also input capture can be used if you wanna, if you have two signals. I told you, I can use only one pin to calculate the time from here to here. I can have one pin. I can calculate the time from here or here. Sometimes you have two signals this way. I want to calculate the time difference between the two signals. In this case, you have to use two pins, apply this one here and apply this one here, 2 pins. And then by this way, I can also get the time difference here. Okay. The last thing here is for our microcontroller, we don't have only one timer, we have 3 timers. Should be very happy. We have 3 timers. So we have timer 2, we have timer 22, 22, 21. So we have 3 timers. Everyone is independent, separate. You get what I'm saying? So we have 3 timers. Every one of them is separate. Not only that, for timer 2, we have 3 channels. So it's 3 channels. Every channel has 1 pin. Okay. Anyway, okay, I'm gonna explain it next time. Okay. I don't want to take more time. Okay, so I'm gonna explain it next time. Okay, guys. But what I want to say, all the time I was explaining, we have 1 timer. In the reality, we have 3 timers, not 1. You get what I'm saying? That means I can use not only that, every timer, so 1 timer has 4 channels. 4 channels. The other 2 timer has 2 channels and 2 channels. Every channel can be input capture or output compare. Oh my goodness, you have too many things. Yes, you have too many things. So for example, one timer will have 4 channels. So I can use all of them output compare or all of them input capture. Okay, you got what I'm saying? So what I'm saying, we have 3 timers. 1 timer that has 4 channels. The other two timer, each one has 2 channels, and every channel you can program it input capture or output compare. So in total, you can have 8 channels. All of them you can make all of them input capture. You can make all of them output compare. Some of them input capture, some of them input. That's why I told you before, microcontroller can do a lot of things. Okay, guys, this is just one system. Still, we have analog to digital converter, we have serial communication, we have a lot of things. You got what I'm saying? So anyway, that's enough for today. Sorry, I took a lot of time.